Good afternoon and welcome to today's electronic design webcast. Our topic today is characterization and compliance testing for 400G PAM4 designs sponsored by Keysight. I'm Chris DiMartino with Penton's Design Engineering and Sourcing Group. Now let's meet today's speaker. Steve Segal is currently the 400G Solution Specialist in the Internet Infrastructure team within the Networking and Data Center Division at Keysight. In this role, he guides the requirements definition for solutions and solution components used for characterization and compliance testing of everything within the data center ecosystem involving 400G class, optical and electrical links. Steve currently represents Keysight in the CEI, that's Common Electrical Interface Project Working Groups within the Optical Internetworking Forum, where he has made several technical contributions to compliance testing specifications and methodology. In the OIF, he also serves as the chair of the Physical and Link Layer Interoperability Working Group. He also is a contributor in the IEEE 802.3bs and 802.3cd projects developing next-generation Ethernet links operating in the range of 50 to 400 gigabits per second. Recently, he has made similar contributions within the 32G Fiber Channel Standard Working Group. Robert Slay is a strategic product planner in Keysight Technologies Network and Data Center Organization. His responsibilities include product development of pulse amplitude modulation PAM4 test solutions based on Keysight's high-speed electrical and optical digital communications analyzer. Robert's experience at Keysight Technologies includes 5 years in technical support and over 12 years in technical marketing. Prior to working at Keysight, Robert worked for 10 years at Westall Telecommunications in Vancouver, British Columbia, Canada, designing microwave and optical telecommunication networks. Robert earned his BSEE degree from the University of Victoria. Now let me turn things over to our presenters. Gentlemen, the floor is yours.
Thank you, Chris. Okay, so this is what we're going to do on an agenda today. We're going to talk about what the state of the standards are. Many of them are very close to being released or have been released. And then we're going to talk about really updates. There's too much material to cover in just an hour on 400G and PAM4 signaling, so we're really going to focus on the updates. Rob's going to cover the transmit side, and I'm going to do the receive side, and then we'll wrap up with questions and answers. So let's start talking about the 400G class standards. I use that word quite a bit, 400G class. And don't just think of Ethernet. Really what this is I like to define it as all of these standards have to do with data center networking that use a lane rate of 50 gigabits per second. So all of them are very similar. Most of them are using PAM4, although we do see some other modulation formats involved. The one that really kicked the whole thing off was the Ethernet IEEE 802.3bs project, 400 gigabit per second. This is single mode fiber optical links along with the chip-to-chip and chip-to-module interfaces. The technical work on this standard is all complete now. It's been complete for a couple of months. It's in the process of a formal balloting and will be published in late spring 2018. So, on the electrical side, OIF CEI, this is a Common Electrical Interface. There's a series of documents there that cover 5 different reaches, everything from die to die on the same chip carrier to backplanes and everything in between. And these standards are in the same state that the technical work is complete, and they'll be published either in very, very late winter or early spring 2018. So it's kind of in the same state as 802.3bs. The remaining active project in Ethernet is the CD project. This is where we bring in the multi-mode fibers. Now this doesn't have a 400G speed, but it has everything below it. And again, it's all 50 gigabit lane rates. It's multiple lanes. And it has its own chip-to-chip and chip-to-module interfaces, as well as adding backplanes and passive cables. And this is entering what they call sponsor ballot stage, which says the draft is getting more firm, so it's more difficult to make significant changes in it. And then the remaining project on the Ethernet side is there's fiber channel project, fiber channel 64G. We just had a meeting here yesterday in Santa Rosa, and I would update the slide just based on yesterday. The third draft that is complete, it's actually draft 4, but it's the third complete draft, is out now. And I think this is going to wrap up in about 6 months. So technical work will be done about the middle of summer, and then it'll go to letter ballot and publication. And then in Ethernet, they just are starting a project to pick up the longest reaches. This is really not inside the data center. It would be a big metro and data center interconnect. And they're trying to get to the 40 kilometer. We had that in 100G and the slower rates, but so far it's not addressed at the higher rates. So there's a project that's just exiting the completion of the study group and be ready to do the project start. What's coming up next is going to be the 800G class, and these will be denoted with lane rates of 100 gigabits per second or slightly greater. And OIF is already actively working on this on the next generation common electrical interfaces. There are 4 reaches defined. 3 of them have formal project starts, and one of them, the VSR, which is the chip to module, already is in its second draft stage, so it has a complete draft out. And then Ethernet will be following up with something very similar to the 802.3bs, but doubling the lane rate, and this will be the 800 gigabit project. We'll be starting with single mode fibers, and that project really won't get started until after BS is published. So that's kind of where the official documents are. You can see they're wrapping up. So what's the general status of folks working with these things and designing to them? Well, we're right to the stage now, we've turned on the individual components in the ecosystem, and we're actually starting to do some total systems where we put, SerDes and host chips with cages and connectors and modules on circuit boards and are turning them on. And, when we do that, as expected with any new standard, there's some issues we're running into, and there's showing that we're going to have to make some changes. It's a little bit tougher with the 400G generation, because with the shift to PAM4, that was a fairly monumental change, and so it's a little bit more difficult than the evolutionary changes we've had in the past. So, the normal things you expect, that the parameter tables in these documents are going to be updated, with changes in TX, RX, as well as channel operating margin parameters. And then several new measurements were defined because we're dealing with PAM4 modulation now. Many of those are on the transmit side, and Rob's going to talk about that, but we're seeing some changes where they've had to go back and make some tweaks to the measurements, which means if you have these embedded in your test instruments, be sure you're always using the latest software version, because these measurements do change, and they are in a state of flux right now. And then actually how we do the testing and some of the test setups are needing to change because of the difference of the modulation, the fact that we're dealing with FEC links, and I'll cover quite a bit of that in the RX section. And with that, I'll just turn it over to Rob.
All right, thank you very much, Steve. Today I'm going to talk to you a little bit about output or transmitter characterization, both on the optical side, some key measurements there, and on the electrical side, with a focus on some of the parameters that are called out in 802.3bs and CD. We'll start with looking at some of the key measurements for optical transmitters, and we'll look back just for a moment at NRZ, or non-return to zero transmitters, and some of the measurements that were made to characterize those outputs. One of them being optical modulation amplitude, or OMA. That's the difference between the 1 power level and the 0 level. Extinction ratio is the ratio of the 1 and 0 level, so it takes into account the DC offset. There's another measurement called transmitter dispersion penalty, or TDP, that we'll talk about. It's a BER-based measurement. And then the very traditional IMASC test, which puts up a standards-based, essentially a keep-out region for the transmitted waveform. On the PAM4 side of things, we've got very similar measurements. There's one called the outer OMA, which is the difference between the 3 level and the 0 level. So if you're looking at that PAM4 signal on the top right hand there, the bottom level is the 0, and then it goes to 1, 2, and 3. So the outer OMA is looking at the bottom and top rail. The outer extinction ratio is the ratio of those 2 levels. And then there's a new measurement called transmitter dispersion eye closure for PAM4. That's TDECQ, and the Q stands for Quaternary. Notice that there is no longer a traditional NRZ mass test, and we'll explore why that is in just a moment. So here's just a reference for you going and looking at the latest draft, which is 802.3BS draft 3.5 from mid-October. And here you can see the summary of outer OMA, outer ER, and TDECQ. So what is TDECQ? Well, it essentially tells you the performance of your transmitter, your device, relative to an ideal transmitter. And if we were to go back and look at the NRZ TDP measurement, this is literally a BER-based measurement where we compared the performance of your transmitter with that of an ideal or golden transmitter. That's a BERT. And what we did was we looked at how much extra power, how much additional power was required at the receiver in order to compensate your device for its non-ideal performance. And the difference between essentially that additional attenuation or power was the TDP value. Because it required quite a bit of test equipment, and it was a BER-based measurement, it was fairly expensive and quite time-consuming to perform that measurement. So standards committee members decided that they wanted a different approach and developed the TDECQ measurement, where we indirectly measure the symbol error ratio using an oscilloscope. And that means that it's a lot more cost-effective, and it's fairly easy and fast to make that measurement compared to the TDP measurement. So this is a block diagram showing the TDECQ measurement. On the top left, you can see your device, your optical transmitter, and it's got to generate an SSPRQ pattern. That's a short stress pattern, repetitive, quaternary, so it's a PAM4 signal that's 2 to the 16 minus 1 symbols long. And that's passed through a variable reflector to control the return loss. It's passed through a test fiber. You may need to filter that signal before it goes into the oscilloscope. In addition, you need to have a clock recovery for your optical signal. And this is because the coherence, if you were just to trigger the DCA or your oscilloscope using a trigger from your pattern generator or from your DUT, for example, you no longer have coherence between or correlation between the trigger signal and the data signal. So you really have to use clock recovery, specified 4 meg loop bandwidth with first order, meaning no peaking in the response. And you also need to have a very well-controlled reference receiver with specified bandwidth depending on the baud rate that you're operating at. And then there's also an equalizer. All of these links are performing on the order of 10 to the minus 4, so they're fairly closed eyes and they need to be opened up in order to be analyzed. So the TDECQ equalizer is a 5-tap T-spaced FFE. We then make a pair of histogram measurements on that PAM4 signal and post-process the signal in order to get the TDECQ result. So let's have a closer look at what's happening as part of that TDECQ measurement. Again, we're leveraging the fact that the link itself, the signal, is operating with a very high symbol error ratio on the order of 2 times 10 to the minus 4. And so the first step that we do is we statistically determine the SER on your signal or on your DUT using an oscilloscope. Rather than attenuate the signal to force errors like we did with TDP, we're now mathematically adding noise to create errors. And we continue to add noise onto the incoming signal until the target SER is observed. So that's on your DUT. The next step, and again, this is all done in post-processing, is to repeat that process for a virtual ideal transmitter. So you don't physically have to have this. It's all done mathematically. But we continue to add noise to that signal with the same OMA as your DUT until we achieve the SER. And then the amount of noise that gets added to the ideal reference receiver in order to reach that target SER is going to be larger than the amount of noise in your DUT. And the difference in those noise levels represents TDECQ. So it becomes a fairly fast and easy measurement to perform. One thing to note that TDECQ measurement has evolved since the start of 802.3BS. Very early TDECQ versions optimized that TDECQ equalizer by trying to minimize the spread on the eye level, so minimize the ISI, and you want a maximum eye opening. In the latest draft 3.5, and again, as Steve said, it's all the technical changes for BS have really been implemented at this point. So what needs to get optimized is the TDECQ number itself, and there's various ways that we're going to do that, and we'll look at those in more depth in a moment. Another change was the BS measurement, or BS standard initially defined a 5-tap T over 2-spaced FFE, and now it's a T-spaced FFE. The standard initially proposed a more traditional Bessel-Thompson bandwidth, which is 75% of the baud rate, and now that's been changed to 50% of the baud rate. In addition, the initial TDECQ definition had 2 time slices in the center of the eye. Now those histograms can be moved. They have the same relationship to one another, but you're allowed to move them slightly within that PAM4 signal. And so this is what's in the latest draft. There's still some discussions for CD about some additional changes that, if implemented, might be rolled back into the BS standard. But note that these changes were made to better represent what a typical system is going to behave like. And so we're really trying to emulate what the real receiver is going to be doing when making this TDECQ measurement. So one of the challenges is trying to find root cause for high TDECQ. So let's say that you've got a TDECQ result and it's higher than you'd expect. Where do you go to try and fix that problem? Well, you really want to start thinking like a receiver. So could it be poor linearity, meaning that each one of the levels is not equally spaced? And if it's not, then the decision threshold at the receiver may not be optimally set, and that could certainly impact your system SER. Skew, if your skew isn't properly aligned, that could also impact SER, as can noise. So TDECQ is fairly new, but there's now starting to become some more advanced analysis capability, which can help you determine what part of your signal is dominating the TDECQ results. So for example, if you could make a partial TDECQ measurement, that would tell you a lot about which eye was most problematic. Likewise, being able to measure SER for each eye and measure noise on each eye in order to determine perhaps you've got a RIN, or relative intensity noise problem, where the noise on your top eye is dominating the SER. Another key to accurate, repeatable TDECQ measurement capability is to ensure that you're using a very well-designed equalizer, your TDECQ equalizer. So you want to have automatic optimization of both tap weights and the main cursor in order to minimize that TDECQ value. And you'd also like, especially for speed purposes, to be able to, once you've determined what your tap values are, to be able to seed your TDECQ equalizer in order to speed the analysis, because right now it's an iterative approach, and it can be fairly time consuming. So if you can shorten that test time, especially in manufacturing, by seeding your TDECQ, that will really help your analysis time. You want to make sure that you're using a reference receiver that applies the correct frequency response for your oscilloscope. And so there's techniques such as the impulse response correction, or IRC, that characterize the non-ideal behavior of your receiver and are able to mathematically correct that. And so what this means is that you're using essentially an ideal receiver from one instrument to the next in order to characterize your DUTs. So you get much better repeatability that way from one instrument to the next. And then you want to make sure that you start out with a very low noise receiver. This will impact your TDECQ results as well. So Keysight has developed, as part of FlexDCA, which is the user interface for the DCA product line, a pair of options, 9FP and 9TP, that provide a very large suite of measurement capability for analyzing TDECQ. One thing to note here is that what we've chosen to do and this is by design, was build these measurements directly into the user interface. And that was done to ensure that we optimized the measurement time. So we reduced the measurement time for you. And you can see that we've got not just TDECQ and outer OMA and ER, but we have all those partial measurements, the partial SER, partial TDECQ implemented as well. From a hardware standpoint, we've optimized the solution for both R&D and manufacturing. So again, we've built that TDECQ measurement capability into the base firmware. The hardware itself samples 6 times faster, this new DCA-M or DCA Mini solution compared to the traditional DCA. And we've implemented this impulse response correction process. That allows us to create an ideal reference receiver. And because we've pulled out the computer, we've pulled out the display, and we've reduced the cost, the manufacturing cost, we're able to pass that cost savings along to you. Very low noise. We have an amplified receiver, so that also is really important in providing accurate and repeatable TDECQ results. On the real-time oscilloscope side, we also have an O-to-E front end, 33 gigahertz O-to-E that can be connected to our real-time series, the V-series, X, Q, and Z-series oscilloscope, and it's very powerful for doing system-level R&D debug and troubleshooting. You can apply the ideal reference receiver, so per the standard, 50% of the baud rate. And we have built into the oscilloscope several NRZ measurements. If you're looking for PAM4 measurements, give us a call, contact your Keysight rep, and we can give you an update on where those are as well. But as you'll hear in a moment, using real-time scopes is a real benefit when trying to capture rare events. So now we're going to transition to some key measurements on the electrical side of things. And some of the measurements that need to get performed, one's called level separation mismatch ratio. This is the linearity, how equally spaced your 4 levels are from one another. Another is called signal to noise and distortion, or SNDR. And even though it's essentially technically sound for BS, there's still some debate over the specs for CD, and if there are changes to this measurement, they may end up getting rolled back into the BS standard. And another set of key measurements is called output jitter. These are JRMS, J4U for uncorrelated, and even and odd jitter, or EOJ. So having a closer look at those, you may think that you recognize a lot of these acronyms. So J4 sounds a lot like J2, J5, J9. EOJ has been around in some earlier standards. So you might think that they're pretty straightforward to measure, when in fact these new IEEE output jitter measurements are made very, very differently than more traditional or past standards. In the past, J4, J5, J9, and EOJ measurements were performed on all edges of an NRZ pattern. For 802.3BS and CD, these measurements are now performed on 12 specific edges of a PRBS 13Q. So the takeaway here is don't just pull out your scope and press the EOJ button on it, because you will not get an accurate result. You need to have very specific software that's going to target those 12 edges, or you have to do that manually. So why did BS make that change? Well, there's recognition that different architectures are used to generate PAM4 signals. And if you have an architecture such as that shown in the diagram, where you have 2 NRZ patterns that are generated from 2 clock buffers or 2 PLLs, it's possible to have different uncorrelated jitter profiles on your MSB and LSB. And as a result of that, if you were only to look at the clock pattern, the JP stands for jitter pattern 0 level to 3 level. This was the original clock pattern that was defined. You could potentially miss some jitter issues. And so that's the reason why we're now, the Standards Committee has changed to looking at 12 specific edges, is to catch these problems that might occur from that type of architecture. So standard specifies which edges you shall make, and initially it was a very time-consuming measurement to make because the standard specified that each 1% histogram had to have 1 million hits in it. So both real-time scopes, because it had to acquire the entire pattern, and sampling scopes, because they sample relatively slowly, they took a long, long time to make this measurement. On the sampling side, it was hours. So early in January, Keysight presented some advanced methods to speed up the test time while maintaining accuracy, and there's a reference that you can go to if you'd like to. But there were two main outcomes. One is the histogram size changed. No longer do you have to have 1 million samples in that histogram. And the other change was some new acquisition methods were accepted, being the edge model technique that I'll tell you about. So the edge model is where we can initially characterize what that edge looks like. So we create an edge model for each of the 12 edges. And then using that edge model, when we acquire a sample, say sample 1, which is high there, we know based on the edge model that through that 1% histogram, that transition actually was early. And likewise with sample 2, if we measured low, we would know where that sample would land in that 1 histogram, and it would be 1% histogram, and it would be late. And so this allows us to be extremely efficient with targeted sampling, and we can make those output jitter measurements very, very quickly now. In fact, that new 12-edge jitter method that's been implemented in FlexDCA has now reduced test time from hours to much less than a minute. It's about 30 seconds. And it can even be faster than that depending on your hardware that you're using. So we measure J4U, JRMS, and even and odd jitter on that PRBS13Q, and we will report not just the parameters that are required by the standard, but we will also report all of the individual results. So if there's something going on a particular transition, you'll be able to see that that particular transition is dominating your result. In addition, on the electrical side, there's a number of custom measurements that need to be performed, such as steady state voltage, SNDR, that's that signal to noise and distortion ratio measurement, ESMW, eye symmetry mask width. So we have developed software to facilitate this. This will automate the oscilloscope, perform the measurement, compare it against the results, and generate a report for both the sampling scope, that's the N1085 app, and our real-time scopes, that's the N8836 36A application. From a hardware standpoint, on the electrical side, if you're using a sampling scope, you'd be using the 86100D with an 86108B plug-in. We also have other plug-ins with remote heads and higher bandwidth capabilities. On the real-time scope, you'd be using the Z-series because it has 63 gigahertz of bandwidth, and that is required in order to achieve the 33 and 40 gigahertz Bessel-Thompson response required by IEEE and CEI. So you might ask yourself, well, boy, you've got a lot of capability there. Which scope do I use to characterize my PAM4 transmitter? And generally speaking, sampling scopes, because of the very low noise, just architecturally, we can have much lower noise on a sampling scope than on a real-time scope. They are going to be best for validating and characterizing PAM4 designs. They're going to give you the most margin when you're making eye width, eye height measurements, for example. But real-time oscilloscopes, they're very important when you're trying to troubleshoot PAM4 designs. They can capture these one-time glitches, and in fact, because of the very high symbol error ratio on these links, they can actually do some error capture and BER or SER performance measurements for you, and they can decode that incoming data stream as well. So real-time scopes have a tremendous amount of capability when it comes to these PAM4 links and are a real key tool to be using. So with that, I'm going to turn things over to Steve, and he's going to talk about input or receiver characterization.
Thanks, Rob. Okay, so I'm going to talk about two main topics here and then go into quite a bit of depth. And one of them is changes in the input test setup. I alluded to that in the introductory slides, that the big thing that we're seeing with PAM4 and links is that they don't run error-free. They rely on real high-gain forward error correction to improve the link. Now, to be honest, that wasn't something entirely new with 400G. We had that in 100G with the backplanes and with one optical standard, the SR4. But for many of you, this is the first time you're dealing with links that don't run error-free by design. And there's a couple of implications of that. First, when you're measuring burr, all of a sudden that number that you read in the for the burr measurement or SIR measurement is important. It has to be an accurate measurement. It has to be a repeatable measurement. Okay, when the links ran non-error-free, basically if you say anything other than 0 in the display, you knew that you had a problem. But now you're not going to see 0 in the display, so you're going to rely on the integrity of that measurement. So that's a big thing. That is a big change that we're seeing now. And the other one is in the test setup. Because these links don't run error-free, we got to think about that loopback link in the BERT. That might not be that's driving the error detector with loopback data. That link itself might not be error-free, and that creates some problems. That's what I'm going to talk about quite a bit. And then I want to just touch a little bit on the importance of aggressor testing. You know, that's been in the standards for a long time that you need to do it. Most people haven't done it in the past, but because of the reduced signal-to-noise ratio that we have with PAM4 links, it's really important not only for the input measurements with a BERT, but the output measurements. We see noticeable eye closure in not only electrical but even optical links with adding the aggressors. So it's important that those be present. So now let's jump into talking about when the links don't run error-free by design and what the implications of that when we're doing input testing. So the bit error rate ratio tester continues to be the principal tool. BERT continues to be the principal tool. And I'm going to spend just a couple of minutes kind of walking through how that setup works. And many of you are familiar with it, but it's really important we understand this to see the context of this, what this issue is. Okay, so we're testing device under test, and we're looking at a receiver or input, and we want to determine its ability to correctly interpret data that has known impairments in it. So the impairments are within the allowed range of the compliance of the transmitter and the channel, and as long as those impairments are within meet that criteria, the input should be able to detect them. And again, you know, in the past it would be error-free. Now it's at a suitable error level. It won't be error-free. So now we're going to put the BERT in into the test setup. So the pattern generator, you know, BERTs have two halves. They have a pattern generator and an error detector. So the pattern generator, its job is to create a data pattern that is stressed. And what stressed is, that means that the impairments are calibrated. We have various mechanisms in the BERT to put noise and jitter stresses into the signal, and quite often we need an external channel or an ISI in the test setup, so that could be a circuit board trace. And then that stress signal goes into the device that we're testing, the input that we're testing. Now, whether or not that receiver makes a correct decision is only known within that device. You know, you got to get that signal out somehow to measure it. Okay, so the way we do that is with loopback, because we need to get that signal back out to measure the burr. So we take the signal out and we route it back through a transmitter in the device, a separate transmitter, and we retransmit that signal through a clean channel or a very clean link into the error detector of the BERT. That's the other half of the BERT. So what the error detector does is it has a replica of the test pattern, and it aligns it in time with the incoming loopback signal, and it compares bit by bit or symbol by symbol, depending if it's NRZ or PAM4, with the replica of the test pattern, counts the total number of bits or symbols and the total number that were incorrect, and does the ratio to determine bit error ratio. So that's the way the BERT works. The key is that part that says clean loopback link. You know, in the past, these links ran error-free, and now, by design, they're not error-free. So what happens if we have errors in that? Well, any error where my arrow is drawn at in that signal caused by any corruption mechanism will be counted by the error detector. So the error could actually be at the input of the error detector itself. So those errors are added to the real errors that the DUT experienced. And once we have that, we confound the results, because we're going to overstate the error rate because we're going to have additional errors produced by the input of the error detector. Okay? So now notice I moved the error. I said that clean link. The clean link now with PAM4 really goes beyond just the cable. We tend to think, well, just use a short cable to get the clean link, but it has a lot to do with the retransmit. It's in the device under test itself, and transmitters themselves in PAM4 are quite often a contributor. When you look at these link margins, error margins, a big contribution is from the nonlinearities and noise and distortions in the transmitter itself. So, you know, that's beyond the control of the BERT to be able to assure that that transmitter is clean. So, you know, the question is, will the loopback link be clean enough, be error-free enough to make an accurate measurement? So let's look at some test scenarios. And in all of these, I'm going to walk through a series of cases, and I'm going to be testing a module, an optical module, and I'm going to be testing an electrical input. So it's the transmit input that receives an electrical signal that drives the TOSA. So it would be driving a VCSEL or, you know, go through a laser driver modulator or whatever, depending on the module configuration. And in a test setup, we'd have a compliance test board. And we're going to start with the 100G case. So this is a legacy 100G, and these links are designed to run error-free. So we have the BERT pattern generator, just as you saw in the previous diagram. And because the link is designed to run error-free, okay, that's what we're testing, that TX input again. We use, quite often, we will use the same module. We'll just take a short optical patch cord and wrap it around from the optical transmit output to the receive input. And then we take that signal and feed that back into the BERT, into the error detector of the BERT. And this all works because of the values in the link. Now, as I just said earlier, that, you know, aggressors are important, and for the sake of simplicity, I don't show them. But to do this test properly, we would have to have aggressors in it. Okay. Now let's look at the numbers in this. So if we're looking at the standard in the 100G case, the chip to module, the BER requirement is essentially error-free. It's 1E15. Now that's not practical to test because that takes days to measure. So it's tested to 1E12. That's what the standard says. We test it to 1E12, and we're looking for error-free operation. Essentially, it is error-free. So now if I take the same standard and I look at the optical loopback, or the optical path plus the chip to module, the entire link, again, is 1E minus 12. That's what the BER criteria is. So essentially, that's error-free. So our loopback path in this case is error-free. And if it's a good module, then we're not going to be adding any additional errors. You know, as long as we have a clean setup and a short cable running between that compliance test board and the error detector input, then this method is going to work fine. And this is the method you've probably been using for years. Okay, so what changes with PAM4? Okay, so let's look at that. It all gets into the numbers. So it's the same test setup, and initially we're going to try it with the optical loopback. Okay, but remember that these don't run error-free. So the test criteria for the chip to module on the host side is only 1E minus 8. Now, quite often they're a bit better than that, but they're not error-free. And so we're going to have some errors in that, and that's what we're trying to measure, again, that TX input. And we do our optical loopback. Well, we take the same standard. We look at our 802.3BS, and we look at all the optical links, optical plus chip to module link. The BER requirement is 2.4E to the minus 4th. So it's worse than the signal we're trying to measure. We could potentially have more errors in the loopback path than we actually have in the signal that we're trying to measure. And I was working with a customer just a few weeks ago that was trying to do this, and initially they were trying this technique with the optical loopback and wondering why it wasn't working, and this is the answer right here. So So you might think, well, okay, you know, that's because the ROSA isn't that great. We know the receivers are challenged, and for PAM4, so let's use an optical or an instrument grade O to E converter. An instrument grade O to E converter is going to have a lot lower noise floor. It might be higher bandwidth. It might have tunable filters. A lot of things that should clean that signal up. Can we still make that measurement? Well, remember I was showing when I showed that arrow getting bigger on where the loopback path is, it includes the transmitter. So yes, this probably does have a bit better burr performance, but there are transmitter distortions. There can be linearity, there can be signal-to-noise ratio problems. Since it's a VCSEL, you're going to have some skew in the eyes. You might have too much skew. So all of those things could contribute to causing some errors at the transmitter within the module of where the optical signal is being transmitted. So this technique, you know, any technique using an optical loopback is suspect in the module. That's a problem. And you can already see where this is going. it's going to say that the existing, modules, if we don't have some special stuff built into the module, testing this particular electrical input is going to be very, very difficult to do or impossible to make this measurement, okay? So now let's look at another approach. And some of the electronics that we've seen, and this customer that I was working with in Asia, they had this very same problem. And they did have this capability in there. After they tried the optical, they tried the electrical. So they have the ability in their interface electronics that drive the Tosa with the host side. Their interface electronics have a test mode that allows a host side loopback. So it takes the TX input signal, and rather than driving the VCSEL driver with it, they wrap that signal around into the received data output, and they retransmit that signal back, okay? And so that's what they were trying to do, and they weren't getting very good results, okay? And we were able to work with that customer and clean some things up, and we actually did get results that were passable, but, it's very iffy, and here's the things. The problem is even with this host side loopback, remember that chip to module link is only specified to work to 1e minus 5. And quite often we see something better than that, but we see numbers in 1e minus 7, 1e minus 8 is on the high end of what they run, and a big artifact in that is a connector. So this technique might work, but you have some caveats that have to be in place. The transmitter has to be really good. You have to have a very linear transmitter, very low noise, very little skew in your VCSEL. Obviously, the channel has to be very short. That's always the case when you're using an air detector. But the other thing that gets to be a problem with these modules is reflections. Reflections going through the module connector to the module compliance board will cause a problem. And in their testing, they actually didn't have this bundled into the module yet. It was still on an evaluation board. They were able to access this signal with a cable, so they were eliminating that connector and using a cleaner connector, and we were able to squeak by and get it to work. But I suspect in the final module, you might have a problem because of the reflections caused by that connector. And then, of course, you have to carefully equalize the bird input. Now, we do have a powerful equalizer in there, and it allows some manual tuning and with some modes that we can get in, and we can see what's going on to do the tuning. And by doing all that, in this particular case, we're able to get acceptable results. But the big question is, how can you assure this? How can you assure that your loopback path really is not introducing significant errors and distorting your measurement? The proper way to do it, and the best way, if you have the hardware to do it, is to build an error checker in the device. Okay, so you just eliminate the loopback path altogether. So in this case, you would have an error checker monitoring the TX receiver and the input. And most of the silicon that does this actually has two error checkers. It has one in each direction, so it can monitor the optical signal as well. So now, again, our required measurement is 1e minus 5, but we're not using the loopback path. We're using the management interface in the module. So the BERT is being used as a pattern generator, but the air detector is not being used in the BERT right now. So that's we get the air count from the air counter built in the module itself, and we do that through the management interface. Now, one of the problems is that you lose a lot of the automations the BERT has in making this measurement, and if you're using our BERT with our software, with our M8070 software, we've alleviated this problem because we're seeing, starting with the host chips, we're seeing a lot of people building air checkers inside, and so we put some tools, and I'll cover that in another slide as to what the advantages of those are. So let's talk about the pros and cons of using internal air checkers. Even if you have them, some people don't like to use them. And there are some trade-offs in it. Now, certainly, because of this loopback issue, it's great. It eliminates all that problem. And if you have one, we really advise you use the internal air checker. That's the best way to go. But the challenges are, the advantages are you're not going to overstate the BERT because you don't have a loopback path. And the other advantage is that you're not just doing a component test. Think about it. If the air checker is built inside, we don't need that module compliance board anymore, right? So we can actually do this in system. So if you're a system integrator, you're building a switch card, and you have your host chip, and you want to test your circuit board layout, make sure that there aren't any reflections on the circuit board that are too bad, and go through the connector, you can test the entire link now and measure that burr, with the assumption that your host chip can generate the correct test pattern, which most of them can. But what are the downsides? Well, the biggest downside is that you're limited on the selection of test patterns that you can use. You have to design the air checker into silicon when you design the chip, and many of them allow more than one pattern to be used, which is useful. But maybe you want to test with a specific pattern because you're looking for a pattern sensitivity or something like that. You might not have the ability to do that with the internal air checker, and it requires a special test mode to go into the air checker, so that's not the mission mode. And just because you're having to reconfigure the data path inside the chip itself, you might be missing some things in the data path that a loopback signal would show. We would see problems with errors being introduced elsewhere in the data path. And then you lose the ability, all these automated measurements such as a jitter tolerance sweep. As I said, if you're relying on the internal air checker, you don't have that capability with some BERTs, but now with our new BERT control software, we have this mode called the DUT control interface, and it allows you to access those internal air counters in your DUT through the management interface if it's a module, and then integrate that, and essentially it substitutes your air counter for our air detector. So all of the measurements such as jitter tolerance that are built into the BERT are accessible to you with this control. And it also is handy because it allows you to control other device registers once we have this interface in place. So it's just nice for troubleshooting in general. So now how can we validate the loop and make sure that the loop really is error-free? Because I said, if you're going to rely on the loopback method, you really have to validate you have an error-free mode or sufficiently error-free. It might not be error-free. It might be, 10. You're measuring 1e minus 5 and you're measuring 1e minus 11 or something. That's close enough that you're several orders of magnitude that you're not going to influence that burr measurement that much. But basically, you have, I went through all these criteria. You have to have a clean transmitter. You have to have low reflections. You have to have a good low loss channel. And so we really need to validate. So here we are. And it's my blue arrow that I put on that. We need to validate that link because we're going to try to use loopback, and we need to validate that really is error-free. So the ideal method to do this is, once again, requires hardware in your chip, and that's to put a pattern generator instead of an air checker. And a pattern generator is easier. It takes much fewer gates to build one. You can build something based on PRBS or QPRBS with a very, very low gate count. Doesn't need up very much of your real estate, but you can put that in your device, and if you have the ability to put a test pattern into the transmitter that is providing the loopback path, then all we have to do is we need to know what that pattern is. We program our air detector to use that as a reference pattern, and then we're actually validating the real the loopback link that you're going to be using for your burr measurement. So if this measures error-free or sufficiently error-free, then you're good to go. Okay, you might not have that method. You might have an internal air checker, but again, you want to test with a different pattern or something. So you're using this mode with the link side loopback, and you're comparing the results now with the internal air checker with the measurement in the air detector inside the bird itself. And this happens to be the mode when I mentioned I was working with this customer in Asia a few weeks ago. This is exactly what they were doing, and they were reporting that their internal air checker was reading a much lower error level than the BERT was. And what's going on? Well, we did some troubleshooting, and all the problems were errors introduced in their loopback link. So that's the alternative. But in both of these cases, you see, you do need to do either of these methods. You do need to have some additional hardware built into your DUT. So if you're going to be building modules or host chips is required by the standards, but modules it's not. But you really need to think about this if you want to measure the burr in the individual parts of the link, you really need to put these additional air checkers and pattern generators into your device when you design the silicon. Okay, now I'm going to spend just a couple minutes real quickly talking about crosstalk aggressors. As I said, we need them for PAM4 because of the reduced signal-to-noise ratio. We lose 9.6 dB when we go from NRZ to PAM4, and that bites us in a lot of ways. and now all of a sudden it's really important that we have those. We need them for both optical and electrical testing. I've actually seen it. I wanted to put it in the slide. I apologize for that. The material I saw was copyrighted. I was not able to get copyright permission to duplicate it. But I actually saw an example with a real optical module where we were making the measurements that Rob talked about. They were measuring the optical output measurements from the PAM4 signal, and when they put a received optical signal back into the module in the receive path, that actually closed the eye, measurable amount, a good amount of eye closure. So it's very important that you do it. Okay, so what are the requirements for aggressors? When we look at the standards, they say that they basically emulate the ideal transmitter. So they're going to have the minimum rise time, and they're going to have the maximum amplitude, and they have to be at the same data rate, and but they can't be phase aligned. They have to be asynchronous to the clock that we're testing. And why is that asynchronous necessary? This is really a key point. A lot of people miss this because if they're using a BERT, they have the clock output, and they want to use that as the clock to drive the aggressor. Well, here's the problem. Okay, so let's look at. I'm going to show this with NRZ just for simplicity. It's easier to see, but it's the same effect with PAM4. So here we have an eye that's in the victim channel that we're looking at, and we put an aggressor. And aggressor, if it's static in phase, it's going to couple energy that at some point in time is going to possibly cause some eye closure based on how much coupling we have. And where in time does that closure occur? It's only a problem if it occurs where the receiver, where the slicer is looking at the input to evaluate the input state. So if it occurs in other places in the eye, like near the transition, as I show here, it's not a problem at all. Now you might say, well, my real device, all my multiple lanes in my back channel, they're all coming off a common clock, so they are going to be synchronous. So what's the problem? Well, the problem is your test environment, even though it's synchronous clock, may have different delays because the cable lengths are different than the trace lengths on your circuit board. So, in a test environment, you might have the situation I show on the left, but in your test environment, the delay is such that it's happening right at the slicer, and it's causing a problem. So by putting a synchronous clock requirement in, what that does is that puts some phase slip, because you're going to have a few parts per million different in any two different clocks. So every time that goes through, when we get the next aggressor edge, it's going to be a slightly different point in time, and you can see it's going to slide through the entire unit interval, and eventually it's going to land up with where the slicer is, and if we've got a problem, you're going to catch it. So that's the reason the standards say you need asynchronicity. Now, that might be a problem, that's expensive. I got to buy another clock source, I got to buy another pattern generator. Well, you might not necessarily need to do that. If you have a multi-channel BERT and your BERT allows you on the second channel to have a separate jitter profile, which some do and some don't. Our new BERT for PAM4 does have this ability. Then you can actually get away with a common clock, and all you need to do is dial sinusoidal jitter in that with an amplitude greater than half a UI to guarantee that you are, passing that transition edge, that aggressor edge through the entire unit interval, and program the lowest frequency you can for your SJ frequency, and that will suffice for the asynchronous. Because again, what we're trying to do is just slip that edge through. So now, one last thing I want to speak on this is use PAM4 as the aggressors. Some people use NRZ. You can use NRZ, but you're greatly overstressing the part. So if you test with NRZ and you pass, fine. But if you fail with NRZ, you might want to find a good PAM4 aggressor waveform and use it, because there's much lower high frequency energy, as you can imagine, since the distribution of transitions they're not all 0330 transitions in a PAM4 signal. Okay, so that's the last thing. And I want to just wrap up showing our tools for this. Our BERT that is really optimized for 400G. This was designed from the ground up to do 400G class. It does native PAM4 as well as NRZ. The PAM4 is not created by taking two NRZ signals and analog combining them as some BERTs do, but we actually do a native generation, so that gives you, you don't have any calibration issues, any skew issues to deal with that. We allow you direct programmability of the linearity, so you can do linearity tests with this, and full range of de-emphasis, and all the capabilities you expect in a full-featured NRZ BERT are present in this bird as well. And on top of that, I show a 4-channel arbitrary waveform generator. It's a real good source for aggressors. And then in some of these standards, you need to inject random interference at the far end of the channel. And so how do you do that? Well, you need a noise source, and you have sufficient crest factor with an AWG-based noise source to do that. It's more than adequate for all the standards to meet compliance. This is a very good way to do the testing. Okay, and that wraps up our presentation. So let's go through the summary, and let Rob start out with.
Sure. Thanks, Steve. So just to summarize, as you've seen with PAM4, there's a number of new measurement challenges that have been introduced, and we are continuing to discover new challenges as we turn on links. So be prepared for additional changes down the road. Key optical transmitter measurements include TDECQ, outer OMA, and outer ER. In order to perform these measurements very quickly and accurately and repeatably, you want to make sure that you're using a solution that has been optimized per the latest standard, and that it has the ability to create an ideal reference receiver using impulse response correction, and that you're starting out with a very low noise receiver. Electrically, key measurements are output jitter, that's the J4U, JRMS, and EOJ, as well as SNDR and isometry mask width. And make sure that when you are making those output jitter measurements that you're focused on those 12 edges. And we do have new capability there as well.
Okay, and on the receive side, quite a bit with the loopback path. Now, you know, your traditional method you've been using a BERT for years and years may not work with these links that do not run air-free by design. So you need to take some special caution if you do have to use loopback to ensure that the loopback path is, the errors are controlled in it. And then internal error checking capability, you know, that's a big way to eliminate the use of the loopback. And with our M8070 BERT control software, we make that really easy, that you don't lose your jitter tolerance measurements just because you're using an internal error checker. And the use of crosstalk aggressors is absolutely imperative, not only in the input testing with BERTs, but the output measurements with the scopes. So we really have to have those in place. And for any more information, you know, we could give you a whole list of things to look for on our web, but the easiest way to find it is just remember one thing, keysight.com/find/PAM4, and that will give you the list of all of our tools and solutions for testing in this application space.
Okay, now on to some questions. Here's our first one. Is there some place I can get the PRBS 13Q test pattern?
I didn't understand the question.
Is it somewhere where you can get the PRBS 13Q test pattern? So that's built into our...
Built into the BERT generators. And if you're asking where you can actually get what the pattern definition is, it would be in the appropriate standards document that would be defined in 802.3BS.
Okay, and we have time for one more question. When will BERT M8040 support FEC encoding and decoding?
Ah, that's a good one. That's a difficult thing to do with BERTs, particularly with multi-channels, because of the, as you probably are aware, there's a very, very high gate count to implement that. But we're working on that. We're going to start out with a single channel implementation, you know, for the single lane variants of CD, and then you'll see that move into multi-channels in the past. But it's not going to be anything short term. Just you know, hold tight and look in the next year sometime, and you'll see some activity there.
Okay, thank you. Now we will reply to any unanswered questions by email within the next day or two. And that concludes today's presentation. On behalf of Electronic Design, I'd like to thank Keysight for sponsoring today's event, and of course all of you for joining. Have a great rest of the day.